Okay. In this topic today, we are going to cover the causes of a loop in layer 2 network and briefly explain how spanning tree protocol works. Now, what's the loop in layer 2 protocol? It's the looping like the looping we have studied in the programming languages, which means one client or one device, let me say, will send a broadcast message. This message will keep looping on the network endlessly. So what we are going to do here, in this case, we are going to affect the network performance. We are going to disturb the network in general. So main reason of the spanning tree protocol is to protect the network from loops. And layer 2 network, not layer 3. I'm not talking about the routing, I'm talking about only the switching network here. So in general, we need a redundancy, redundant links. Redundancy is an important part in any network design in order to eliminate a single point of failure and preventing disruption of network services to the users. In case users got a single link, so if this link down, no services for the users. So the redundant or the redundancy is very important in this case, but at the same time, the redundancy will be the main cause of the loop in layer 2 network. So we need to have a redundancy without local loops within layer 2 networks. How we can do this? We will use the spanning tree protocol. So redundant network requires the additional physical path, as you see. But logical redundancy must be a part of the design in this case. So having alternative or alternate physical path for the data to traverse the network make it possible for the user to access the resources regardless of the path disruption. For example, we have 2 or 3 alternative paths. We are using the first one. The first one is down. User can continue accessing the services and the resources without any problem because we have alternate path. And this is the main, actually, any network design, main points. So redundant path in a switched Ethernet network may cause both physical, I'm talking about the hardware now, physical path and logical redundancy loop. So Ethernet LANs require a loop-free topology. We need any topology to eliminate the local loop, to eliminate the loop inside the LAN, where we will use a single path only between any 2 devices, but we will still have a redundant path. So a loop in the Ethernet LAN can cause continued propagation of Ethernet frame until a link is disrupted and break the loop. So this is the main point of the spanning tree protocol. Now let me explain to you what I mean by loop here. Let us assume BC1 send a packet and it's a broadcast packet. So BC1 will send it to S2. S2 what will do? Forward the message to all ports except of the ingress F011. Now MAC table on S2 that BC1 connected to which port F011. Now S2 will forward it to BC2, BC3, S3 and S1. Now S3 will update the MAC table of BC1 to be on Fast Ethernet 02 and S1 on Fast Ethernet 01. Now it's a broadcast, so S3 will send it to S1. S1 will send it to S3 and BC4. Now S3 received the broadcast packet from S1, will forward it back to S2. S2 will send it back to the all connected ports. Same scenario. When we send from S3 to S1, S1 will forward it to all ports except of the ingress, so it will be sent back to S2. Now S2 should update the MAC table. So we will have in this case unstable MAC address table, which means the switch will not know exactly which port belongs to which MAC address table. And the message will be keep looping inside the network. What's the redundancy? As you see here, this is a redundant link. Between S1 and S3, we have two links. We have this one, so I can access S1, then I can access through S1, S3. Or I can use a different path from S2 to S3, from S3 to S1. So spanning tree protocol is a loop prevention network protocol that allow for a redundancy while creating loop-free topology, which means in a spanning tree we will allow for a redundant link between the switches, but without allowing for the loop problem to be occurred on the network. So simply STP or spanning tree protocol logically will block physical loops in layer 2 network, preventing a frame from circling the network forever. Means spanning tree protocol will block port 2 on S3. So once port 3 receive a broadcast message, it will not send it back to S2 in this case. So not allow for what? For the layer 2 or the LAN loop in this case. So simply spanning tree protocol will ensure that there is only a single link between the devices is active. Any other redundant link will be blocked. So in this scenario, this connection or this path between S3 and S2 will be blocked, but we still can access all the network devices. So what's the recalculation? In case the physical connection between S2 and S1 got any failure, the blocked path will become an active path. So users will remain getting access to the network resources. So spanning tree protocol compensates for the failure in the network by recalculating and opening the previously blocked port. Which port? F02. This one is blocked, not this one. We are blocking at S3. So in case trunk 1 connection got a problem, and remember, between the switches, the access mode should be trunk. Between a PC and the switch, it's an access, not trunk mode. So in case we have any failure with the trunk 1, spanning tree protocol will perform a process called recalculation and activate the redundant path or link. So what are the main issues in the context of the redundant switch link? Now, path redundancy provides multiple network services by eliminating the possibility of a single point failure. Means, when multiple paths exist between two devices in Ethernet network, and there is no spanning tree implementation, we have a redundant. So without blocking, without spanning tree implementation on the switch, layer 2 simply will occur. So layer 2 loop can result on what? MAC address instability. Every switch will keep updating the MAC address for each packet it receives. Link saturation, flooding, high CPU utilization because the switch needs to update the MAC address. And in device resulting in the network becomes unusable. So the final result of the loop, we have unusable network. So in general, layer 2 Ethernet does not include any mechanism to recognize and eliminate the endlessly looping frames. In the context of IPv4 and IPv6, we have a mechanism in order to limit the total number of times. The number of times layer 3 now network device can retransmit the packets. So when we talk about IPv4, we will use the time to live for every IPv4 packets to eliminate the endlessly looping, and for IPv6 we are going to use the hub limit. So at each time or at each hub it will be decremented by 1. So once TTL or hub limit reach 0, what the switch will do, or what the router will do, sorry, layer 3 switch or the router, simply it will drop the packet. So we are already handling the loop problem on layer 3 network without any problem. But Ethernet and Ethernet switches, which is operating at layer 2, do not have any comparable mechanism. In order to limit the number of times the switch can retransmit layer 2 frame. So spanning tree protocol was developed in order to prevent the loop to be happened for layer 2 Ethernet. So is it clear what's the main idea why we need the spanning tree protocol? واضح الفكرة؟ We need to eliminate the local loop. We'll have a redundant link, but only a single one will be active. And the other path between the switches depends on some algorithm will be in the block state. Now, what's the loops? What's the problem of the loop now? As we have discussed before, without spanning tree protocol enabled, layer 2 loops can form, causing a broadcast packets, multicast, and unknown unicast frames to loop endlessly. So any broadcast packet, multicast, or unknown unicast, because we need to issue an ARP request in this case, okay, will be what? Endlessly in the loop state. So this simply can break the network or bring the network down quickly. Network overloaded, flooded, we cannot access any services. So it's like the denial of service attack and somehow. So when a loop occurs, the MAC address table on the switch will be constantly changed with the updates from the broadcast frame, which will result that MAC database instability or unstable. Another way, we will not know which port exactly is the port of PC1 because we will receive it in F01, F02, F02, F01, F011. So we'll have unstable MAC table in the case of the loop at layer 2. So this can also, instability of the MAC table can cause a high CPU utilization, which make the switch unable to forward the frames. Also, any unknown unicast frame is when the switch does not have the destination MAC address in its MAC table. It must forward it to all frames out except of the ingress. So how we handle the unknown unicast MAC table? Simply will forward the packets to all ports except of the ingress port. In case we have a redundant link without loops prevention method, we have a loop case scenario here inside the network. Now, what's the broadcast storm? Broadcast storm is an abnormally high number of broadcast overwhelming the network during a specific amount of time. We are continuing talking about the loop case, by the way, scenario and how the broadcast will affect the network performance. Broadcast storms disable the network within a second by overwhelming the switch and end devices. So it can cause by the hardware problem, it can be such as an IC problem, or it can be caused by layer 2 loop in the network. So layer 2 broadcast in the network such as ARP request are very common. So in case of the multicast, layer 2 multicast are typically forwarded the same way as the broadcast by the switch. IPv6 packets are never forwarded as layer 2 broadcast. ICMP v6 neighbor discovery uses layer 2 multicast. Now, host code in layer 2 loop is not accessible to the other host in the network due to the constant changes of the MAC address table, MAC address instability, the one we talked about it before. The switch will not know which port to forward the unicast frame. This is another problem. So in order to prevent the broadcast inside the loop or the broadcast storm in general, in order to prevent the problem of the MAC address table instability, we should implement one of the spanning tree algorithm, let me say, or techniques. So spanning tree is enabled by default on Cisco switches to prevent layer 2 loops from occurring. Now, please focus here. What's the STA, spanning tree algorithm? Now, STB is based on an algorithm. It's a brief introduction invented by Radia Bierman while working for the Digital Equipment Corporation and published in the 1985 in a paper with the title An Algorithm for Distributed Computation of the Spanning Tree in an Extended LAN. So this is the main name or the name of the actually inventor of the STB algorithm. Now, here spanning tree algorithm will create a loop free by. Now this is the, let me say, steps will be applied on the network in order to prevent the loop or layer 2 loops to occur in the network. So STA will create a loop free topology. Loop free means we have a redundant link on the network, but only one link is active by selecting a single route bridge. It can be a step 1. Now, all other switches will determine only single least cost path to the route bridge switch. So we need to select one of the switches as route bridge switch. Now, all other switches will declare or identify a single least cost path to the route bridge switch. So STB prevents the loop from occurring by configuring the loop-free path through the network using strategically placed blocking state ports. Means we'll have only a single path to the route bridge. If there is any alternate path from the same switch to the route bridge, it will be disabled by the blocking state. Will block that port. So the switches running spanning tree protocol are able to compensate for any failure by dynamically unblocking the previously blocked port and permitting the traffic to traverse the alternate path. So in this scenario, here, if this one is the route bridge, so we have a single path between all the switches to the route bridge. Now, one is active the other path, this one in the block state. In case we have any failure here, the alternate path will be on the what? Unblock state, which means it will be changed to the forward state. But we need to recalculate or apply some recalculation in this scenario. So this is the main idea of the spanning tree protocol. Now, how the spanning tree algorithm create a loop-free topology? What are the steps of the STA? Now, we have simple steps. First one, we need to select a root bridge switch. This bridge or this switch is the reference point for the entire network to build a spanning tree around. Each switch will determine a single least cost path from itself to the root bridge. In this topology, all the links are equal cost. Equal cost means with the same bandwidth in this scenario. So what we need here, we need to select one of the switches as a root bridge. Now all the other switches will consider this one as a reference, and they need to declare or determine a single least cost path from the other switches to this switch, to the root bridge. Step 2, block redundant path. So STB will ensure that there is only one logical path. Only one logical path between all destinations on the network by intentionally blocking the redundant path. That could be the main cause of the loop problem. So when the port is blocked, user data is prevented from entering or leaving that port. Once the port is in the block state, the port will not accept or send any user data. Step 3, once we have applied the condition 1 and 2, we will have a loop-free topology, loop-free network. So the blocked port or a blocked port has the effect of making that link non-forwarding link between two switches, any block port in the non-forwarding state. So this will create a topology where each switch will have only a single path to the root bridge, similar to branches on the tree that connects to the root of the tree. So once we have done with the select the root bridge, identify the single least cost path, block any redundant path between the switch and the root bridge switch, we will have or we will come out with a loop-free topology on the network. Now, finally, sometimes we'll need to reapply or calculation in case if link 1 is down, the blocked link should be what? Unblocked. So we need to apply a recalculation here. Physical paths still exist to provide a redundancy, but these paths are disabled or blocked to prevent the loops to be echoed. Now, if the path is ever needed to compensate for the network cable switch failure, so suppose this path is needed because the main one got a cabling failure problem. So spanning tree protocol in this scenario will recalculate the path and unblock the necessary ports to allow the redundant path to become an active path or in a forwarding state. So STB recalculation can also occur in any time a new switch or a new inter-switch link is added to the network. So in case we need to identify a different path, in this scenario, we need to apply a recalculation. Now, let us assume we have this topology or this scenario. Now, the root bridge switch is S1. As you see, all other switches will select only a single least cost path. to the root bridge. Now we have a redundant path here. All these redundant paths will be on the blocked state to prevent the loop to be occurs in the network. So this is simply the main goal of the spanning tree. Now, in case, for example, the path between S5 and S1, which is the root bridge, is down, and for any reason, we will unblock the alternate path, and it will be, or sorry, even in case this one, we are going to activate the blocked port between 5 and S3, so we can still having a spanning tree loop-free topology. In this scenario, we have a failure here between S4 and S2, so this blocked port is blocked and its status changes to be a forwarding port, while if it's in a blocked state, it will not accept, it will not forward any user data. Any question? في عندكم أي استفسارات إلى الآن؟ طيب, now let us talk about the operation. How we will select the root bridge, how we will select a single path between all the switches to the root bridge switch, and the port status as well. Now, using the spanning tree algorithm, STB builds a loop-free topology in 4 steps process. We need to follow these 4 steps in order to come out with a loop-free topology in our network. Step 1, we need to elect a root bridge switch. We need to select one of the switches as a root bridge, but it will be like an election process. يعني زي انتخاب. We need to elect the root port. Every switch will have one root port, except of the root bridge switch. We'll talk about it later. Step 3, select or elect designated port. Step 4, elect alternate or blocked ports. So once we're done with all of these steps, we have a loop-free topology in our network. So during the STA and STB function, the switches will use a bridge protocol data units. This one is very important to share information about themselves and their connection. Bridge protocol data units are used to elect the root bridge. We'll use it on the election of the root bridge, root ports, designated ports, and alternate ports. In other way, switches will talk with each other by sending and receiving bridge protocol data units. So each PPDU contains, now what we have in each bridge protocol data unit? A bridge ID. It's very important here, please focus. That identify the switch, send the bridge protocol data unit. BID will be involved in making many of the STA decisions, including the root bridge and the port rules. We'll use the BID to select somehow or to elect the root bridge, also to elect the root ports as well. Is it a root port, designated port, or alternate port? We have 3 types of ports here. The bridge IT will contain 3 fields actually. Priority value, MAC address of the Ethernet, switch port, and extended ID system or extended system ID. Now, the lowest bridge ID value is determined by combining these three fields. So how we can calculate the bridge ID value? By combining the priority value, MAC address, and extended system ID. So switches will exchange information by using a bridge protocol data unit. It will be used during the election process of the root bridge, root port, designated port, and alternate ports. Bridge ID is very important. It will be included in every bridge protocol data unit and will be used as a reference to make a decision about the root bridge and the port rule. When I say port rule, is this port is a root bridge, designated port, or alternate port. Usually bridge ID containing three fields: priority, MAC, extended ID system. So let us talk about the bridge ID field before we start talking about each step separately. Bridge priority. For the bridge priority field, it's 4 bits field. It has a default value. So the default priority value for all Cisco switches is the decimal value 32768. The range of the values between 0 and 61440, the increment or its increment of 4096. Now, lower bridge priority is preferable. Always the lower value or the lower priority is the preferable one. A bridge priority of 0 takes a precedence over all the other bridge priorities. If it's 0, it's the best case here, bridge priority scenario. Extended ID system or extended system ID value is a decimal value added to the bridge priority value. So we'll add the bridge priority plus the extended system ID in the BID to identify the VLAN of this bridge protocol data unit. In other way, it's the bridge priority plus the VLAN ID. Simply. MAC address, when two switches are configured with the same priority and have the same extended system ID. So the switch having the MAC address with the lowest value expressed in hexadecimal will have the lower bridge ID. Means, suppose we have two switches having the same priority, the same extended ID system. So which one will be the root bridge? We cannot decide. So we'll refer to the MAC address table. Lowest MAC address hexadecimal number will take the advantages over the other switch. And we'll see a scenario about this. Now, let us apply the steps of the spanning tree operation. First step, elect the root bridge. Now, with reference to this scenario, we have three switches. We have details about the priority. As you see, the priority ID of all the switches and the MAC address already declared on the figure. So priority for S3, 32769, for S1, 24577, for S2, 32769. Now, STA or spanning tree algorithm designates a single switch as a root bridge. We need to select or to elect a single switch as a root bridge switch. And this switch will be used as a reference point to all path calculation. So S2 will calculate the least cost path. with reference to the root bridge. S3 will do the same scenario. So usually switches exchange a bridge protocol data units to build a loop-free topology, beginning with selecting the root bridge. First step, we need to elect or select root bridge switch. Now all switches in the broadcast domain. So here all of these switches on the same broadcast domain will participate on the election process. After the switch boot, usually it begins to send the PBDU frames every 2 seconds. This one is important. Now this bridge protocol data unit frame will contain the bridge ID of the sending switch and the bridge ID of the root and the BID or the bridge ID of the root bridge, known as root ID. Now, at the beginning, every switch will consider itself as a root bridge. So the switch now with the lowest bridge ID will become the root bridge. At first, all switches declare themselves as a root bridge with their own bridge ID set as a root ID. Because of this, we say they will send the root ID as well. Eventually, the switches will learn through exchanging the bridge protocol data unit, which switch has the lowest, the smallest bridge ID value, and all the switches will agree that this switch with the lowest BID will be the root bridge. So simply S1, S3, S2 will exchange in this scenario PBDU. After exchanging the PBDU, all of the switches will agree that S1 having the lowest bridge ID value, as you see, 24,577. So all the switches in this scenario will agree that S1 is the root bridge here. واضح? Do you have any question here? Now it might be a scenario in the final exam. They will give you a scenario and they will ask you to identify the root bridge, the designated port, the block port, the root ports. Do you have any question until now? Now next step. What if we have same bridge priority for all the switches as we have in this scenario? So because of the default bridge ID value, we say that the bridge ID default value for every switch is 32,768. It's possible in this case for 2 or more switches to have the same priority as we have in this scenario. In this scenario, where priorities are the same, the switch with the lowest MAC address will become the root bridge. The administrator should configure the desired root bridge switch with a lower priority. So on this figure, all the switches configured with the same priority. Now the default priority is 32,768. Why the priority here is 32,769? Remember, priority plus VLAN ID. Actually, it's the default VLAN 1. So 32,768 plus 1, the VLAN assignment. So the default value here is 32,769. Now all the switches with the same ID. So we cannot, by using the bridge ID, determine or elect the root switch, the root bridge switch. So what we will do in this case, MAC address will be the deciding factor. So we'll select the switch with the lowest MAC address value or hexadecimal MAC address as a root bridge. So as you see, the MAC address of S3 is provided. MAC address of S1 and MAC address of S2. According to the MAC address, the lowest, the smallest MAC address hexadecimal value is the value of S2. So S2 here will be elected as a root bridge for the spanning tree protocol. So first of all, we need to check the, never mind, no problem. First step, we are going to check the bridge ID. Lowest one will be the root bridge. In case all the bridge ID having the same priority value, we are going to use the MAC address in order to decide which a switch is a root bridge switch. Now, step 2. So we have electing now done with the election and select already a root bridge switch. Switch or step 2, sorry, we need to determine the root path cost. When the root bridge has been elected for a given spanning tree instance, the spanning tree algorithm start determining the best path of the root bridge for all destination in the broadcast. Every single switch will calculate the best root path cost from that switch to the root bridge switch. Path information usually called or known as internal root path cost. And usually it's determined by finding the total summation, the total sum of all individual board costs along the path from the switch to the root bridge. So we need to calculate the cost per board. So simply it's the sum of board cost along the path from that switch to the root bridge. So when the switch receives PBDU, it will add the ingress board cost of the segment to determine the internal root path cost. By default, we have a default board cost defined by the speed at which board operates. Now, depending on the board speed, we have a default cost for each board. So as you see in this table, default board cost suggested by Cisco or by IEEE. Cisco switches by default uses the value as defined by IEEE 802.1d standard, also known as a short path cost for both spanning tree protocol and rapid spanning tree protocol. Switchboards have the default board cost associated with their. The board cost is configurable, which means we can configure the board cost as well by the administrator. Now, default value are the following, or default cost. If we are using a spanning tree protocol, according to the IEEE 802.1d standard, 10 gigabit board, the cost is 2, 1 gigabit cost is 4, 100 megabit board cost is 19, 10 megabits per second board cost is 100. Now, if the spanning tree version implemented in the network is the rapid spanning tree protocol according to the different standards IEEE 802.1W, as you see in 2004. 10 gigabit board cost is 200, 1 gigabit 20, 100, 200,000, 10 megabit 2 million. Now, simply how we will determine the route path cost. We will see how many boards between this switch and the route bridge. And we will calculate the best route path cost by find the summation of the board cost with reference to this table. So let us see a scenario here. Now, suppose S1 was elected as a route bridge. Now, step 2, every single switch need to calculate the cost, the internal route path cost. So, we do not have any problem between S3 and S1. We have only one fast Ethernet port. So, what's the cost? Fast Ethernet, the cost is 19. Now, so there is no problem. What about S2? What about S2? Now, S2 has two redundant paths to the route bridge. So we need to calculate the cost of each one. We have a direct path, so a single port here F01. So the cost of this path, path 1, will be 19. And we have alternative path. The different path is from S2 to S3, from S3 to S1. So how many ports? 1, 2. So it's 19 plus 19 according to the spanning tree cost. So the cost of the alternate path, this one, is 32. So we'll select the best internal route path cost in this case. And the port from the switch S2 to S1 will be route port. S3, S1, it will be also route port because all the ports on the route bridge switch always designated ports. So now here we are talking about the cost. So we need to check the cost of each path. And in this case, lowest cost will be the preferred path. In this scenario, we have two different paths between S2 and the route bridge. Lowest cost is the first path, path 1, so will be selected as a what? As a main or a trunk link. Now, always, okay, when we select the path from the other switch to the route bridge, the port on that switch will be a route port. So, in this scenario, F01 will be what? A route port. F02 on S3, a route port. Now, all the ports on S2, which is a route bridge, designated ports. Same in this scenario. Suppose this path and this path. So F01 route port, F01 route port. Now here, route port, because it's designated port. Now we'll not talk about this. Now, route port, we'll talk about this later, route port. Now, Step number 3. So one more time. For the path that's selected from that switch to the root bridge switch, the port will be a root port. Now, every segment between two switches will have one designated port. The designated port is a port of the segment that has internal root path goes to the root bridge. In other words, the designated port has the best path to receive the traffic leading to the root bridge. Now, when the root or what is not a root port, if the port is not a root port or designated port, it will become alternate or blocked port. If it's not root or designated port. The end result, is a single path from every switch to the root bridge. Now, how we will select the designated port and the root port and the alternate port? Simply, we have set of rules. Step 1 or rule 1, all ports on the root bridge are designated port. So F02, F01, F03 designated ports. Because S1 is the root bridge. If one of the end segments is a root port, the other is designated between any switches. If one end is a root, the other one by default is what? Designated. So here, root designated, root designated. Now we'll not say root designated between S2 and S3. We have something here to be discussed because this one alternate port or path. Now all ports attached to the end device are designated ports. So F011 designated port, F018, F06, F03. On segment between two switches, whether neither of the switch is a root port or root bridge, the port on the switch with the least cost path to the root bridge is designated port. What we are saying here, one more time, if we have two switches linked and none of the switches is a root bridge, the port on the switch with the least cost path to the root bridge will be designated port. So this is the scenario. So this is here applied to this scenario, this case. So now both S2 and S3 have the same path cost to the root bridge. The spanning tree algorithm will use the bridge ID as a breaking tie in this scenario. Although not shown in the figure, S2 now has a lower PID. Therefore, fast Ethernet 02 port of S2, not S3, will be chosen as designated port. What about the other port? It will not be a root port, it will be alternate port, a blocked port. So, simply, let me conclude it to you quickly and easily. If it's a root bridge, all the ports designated port. If it's the path between the other switch and the root bridge, so once we have designated, the other side will be a root port. In case the link between the switches is not to the root bridge, lower or lowest bridge ID will be designated port and the other one will be alternate port, not root port. Because every single switch, as you see, have a single root port, one root port. So if the port is not root port or designated port, as we see here, we are talking about the port between S3 and S1. So if it's not a root port or designated port, then it will become alternate or backup ports. Alternate ports are always in discarding or blocking state to prevent the loop. So in this figure, the port on S3 F02 will be on what? On the disabled or the blocked state. So port F02 on S3 is in a blocking state and will not forward Ethernet frames. All other inter-switch ports are in forwarding state. This is the loop prevention part of the spanning tree protocol. As you see, we have a single path between all the network devices, let me say, or switches, and the root bridge port. Switch. Now, how we will select which port from multiple ports as a root port? If I have a multiple ports on the switch, which port will be the root port in this scenario? 1 second, please. Now, in case the switch have a multiple equal cost path to the root bridge. We have multiple paths between the switch and the root bridge switch, and all of them with the same cost. The switch will determine the port by using the following criteria. We will going to use one of these criteria in order to select the root port. The switch will determine the port by using the following. One of the following: lowest sender bridge ID. As you see, sender will depend on the sender. Lowest sender port priority or lowest sender port ID. So let us discuss each one of these. Always the sender. Now, lowest sender bridge ID. In this topology, as you see, we have 4 switches, and S1 was elected as a root bridge. So we do not have any problem between the link between S3 and S1, since this one is designated, this one is a root port. Between S4 and S1, designated port always, so this one will be a root port. Now we have a problem. We have 2 equally cost paths to the root bridge. S2, S3, S1, or S2, S4, S1. So what we will do in this scenario? What we will do? Now, the problem here that S2 has 2 ports, F01 and F02, and both of them with equal cost path to the root bridge. We calculate the cost, same cost. So now the bridge ID of the sender, the sender here is what? S3 or S4. So the bridge ID of the sender will be used to break this tie, this problem. What is this called? Sender's bridge ID. So S3, as you see here, has the ID provided here, and S4 has this bridge ID. So when we compare both of the senders, why we call it a sender? Because we are going to send from S2 to S3. S3 is a sender to S1. So we will depend on the sender bridge ID. The lowest one will be selected as a sender switch, so the port to the lowest bridge ID will be the root port. So because in this scenario S4 has the lower bridge ID, F01 on S2 will be selected as root port. Now, what about the other port? Will be in a blocked state, so alternate port, and F02 is the designated port on S3. So once S2 is a root port, the other port by default will be designated. F03 is a root port, by default in S1 designated. All ports on root bridge designated, so the other one is root port. Case number 2, lowest sender port priority. Lowest sender port priority. This topology now, as you see here, has two switches which are connected with two equal coast paths between them. Now, S1 is the root bridge. So both of its ports are designated ports. So F01 is designated and F02 designated port. So we need to select one of these two ports as what? As a root port on S4. So S4 has two ports, and both of these ports are equal coast path to the root bridge. Because both ports are connected to the same switch, the sender's bridge ID of S1 is equal. So the first step here is a tie. We cannot use this. Same bridge ID on S4 port 6 and S4 port 5. So next is the sender's S1 port priority. The default priority is 128. So both here, both port on S1 have the same priority. This is also tie. But if one of these ports, if either ports on S1, F01 or F02 was configured with a lower port priority, S4 put its adjacent port in forwarding state. The other port on S4 would be a blocking state, which means let us assume that we have configured F01 with a priority less than 128. So in this scenario, F01 is the lower priority. So F01 will be selected as designated port. It's already designated port. So F06 will be the root port. What about F05? Blocked. Alternate state or blocking state. Last scenario, lowest sender port ID. The sender port ID. The last type breaker is the lowest sender port ID. So here, same scenario, switch S4 has received a bridge protocol data unit from port 01 and port 02 on S1. Now both ports, because this one is a root bridge, designated port, so we need to select one of these as root port. The decision here will be based on the sender's port ID. Why? Not the receiver port ID. Before that, we need to select. Can we depend on the sender bridge ID? No, same. Can we depend on the sender port priority? No, because they are same. Now we will use the sender port ID. The ID of the port. As you see, ID1, ID2. So 1 less than 2. So 1 will be selected. So F06 is what here? The root port. Because the port ID of F01 on S1 is lower than F02, port F06 in the switch will be the root port. This port on S04 that is connected to F01 port on S1. Now, so we cannot depend on the sender ID. We cannot depend on the sender priority. They are the same, 128, 128. So we'll check the sender port ID. This ID, port 1, port 2, port 3, port 4. So 1 is the lowest ID. 1 will be selected, so F06 is the root port in this scenario. F05 will be alternate port or in the blocked state. Now, spanning tree convergence requires 3 timers as follows. Now, before we talk about the convergence, or before we talk about the timers, sorry, what's the convergence? It's the process for the board to switch or to move from the disabled state to the forwarding state. We call it convergence. It was blocked, disabled, now it's active and can forward bridge protocol data unit. So usually convergence will require the 3 timers: hello timer, forward delay timer, and max age timer. Hello time is the intervals between the bridge protocol data unit, and we have already mentioned this, that switches will exchange the PBDU every 2 seconds. Every 2 seconds. But this time can be modified between 1 and 10 seconds as well. Now, forward delay timer. Forward delay timer is the time that is spent in the listening and learning state. So the switch port will move to the listening state, learning state. Now the default is 15 seconds for each state. For the listening 15, for the learning 15. And it can be modified to be between 4 and 30. Finally, max age timer. It's the max age, the maximum length of a time the switch will wait before start attempting to change the topology. To switch, to convert from the blocking non-forwarding state to the active state in case we have a path failure scenario. The default is 20 seconds, but it can be modified between 6 and 40 seconds as well. Now, keep in your mind, default times can be changed on the route bridge, which indicate the value of these 3 timers. Now, بالله ركزوا هنا. Spanning tree protocol, timers and port state. STB facilitates the logical loop free path through the broadcast domain. Spanning tree protocol is determined through the information learned by exchanging the PBDU frames between the interconnected switch. Now, if the board, in case the board transition change directly without going through the states from the blocking state to the forwarding state, without any information about the topology, without go through the learning and the listening state, this port can cause the data loop in the network. It can be a reason for the local or the loop to be a course in the network. So because of this reason, we have 5 port states on the spanning tree protocol. 4 of which are operational port state, and 1 is disabled, which means port is non-operational. The port will not send or receive anything. So the disabled state means it's not operational. Now, what are the 4 operational states? Blocking, listening, learning, forwarding. On the blocking state, the protocol or the board, will not exchange a bridge protocol data unit. It will not receive, it will not send. Maximum age timer is 20 seconds. In case we have wait this time, we can now move to the next state, listening. In the listening, who depends on the forward delay time, it's 15 seconds by default. From the listening to the learning, the delay default time is 15 seconds. Once we're done with the learning, the board can now be activated on the forwarding state. So let us summarize this scenario of the transition process by using this table. So this table simply summarizes the operational details for each port state. If the port in a blocking state, the port will receive only a bridge protocol data unit. MAC address table will not update it at all, and the port will not forward any data frame. On listening state, the port can exchange here, learning, listening, a bridge protocol data unit. MAC table will not be updated. Data will not be forwarded at all. Now, on the learning, we can send and receive bridge protocol data unit. MAC table entry will be start updated. No frame data forward. Finally, forwarding state, port can send and receive bridge protocol data unit, updating MAC address table. As you see here, forward data frames, yes, only on the forwarding state. Now, if it's disabled, the port will not send and receive any bridge protocol data unit, no update for the MAC table, no forwarding or sending, no forwarding, sorry, of data frame. So 5 different port states, 4 operational, 1 non-operational, according to the provided table. Now, finally, about the SPANG 3 operation, we need to talk about the pair VLAN SPANG 3, PVST, and you will study it in full details in T216A, by the way. So SPANG 3 protocol can be configured to operate in environments with multiple VLANs, not a single VLAN. In pair VLAN SPANG 3 PVST version of a spanning 3 protocol, we have a different versions, by the way, to the spanning 3 protocol. There is a route bridge elected for each spanning 3 instance, multiple VLANs, route bridge for each one. This makes it possible to have different route bridges for different set of VLANs. Spanning 3 protocol operates as a separate instance of STB for each VLAN. If all ports on all switch are membered on VLAN 1, then we have only one spanning 3 instance or spanning 3 protocol. So SPVT allow me to elect a route bridge for each VLAN on my network. In case we have one VLAN, we have one spanning 3 instance, we have one route bridge network. عندكم أي استفسار الآن؟
لا شكرا.
أهم شيء كيف نختار الروت بريدج، كيف نختار البورت الديزيجنيتد بورت، الستاتس والالتيرنت بورت. هذا مهم جدا الموضوع. انتبهوا. طيب, now let us talk about the evolution of spanning 3 protocol. Let me simplify it to you. We have a multiple versions, not one version for the spanning 3 protocol. Usually, many professionals in general using the spanning 3 STB to refer to the different implementation, various implementation of a spanning 3. Now we are keep saying STB, STB. in general to refer to the implementation, not the version that implement the spanning tree protocol. So for example, we have many versions like rapid spanning tree protocol, multiple spanning tree protocol, pair VLAN spanning tree protocol plus, and many other versions. Now, usually we refer to the implementation by using a spanning tree protocol. Now, IEEE or the latest IEEE documentation or standard documentation on a spanning tree protocol was IEEE 8021D, published in 2004, says the following. STB now has been superseded by a spanning tree protocol, which means rapid spanning tree protocol most widely now used in the network, not STB. Superseded. So the IEEE uses STB to refer to the original implementation of a spanning tree protocol. RSTB, Rapid Spanning Tree Protocol, describe the version of a spanning tree specified in IEEE 802.1D standard. If you have seen here, I think of one of the previous slides, we have mentioned the standard 1D, and there is, as you see, 1D. This is the STB, RSTB 1W standard on this table. So, because of two protocols, STB and RSTB, are similar or sharing the same terminology and method for the loop-free path, the primary focus will be the current standard and Cisco proprietary implementation of STB and RSTB. Cisco switches running iOS 15.5 or later runs the pair VLAN spanning tree protocol plus by default. This version incorporates many of the specifications of IEEE standards, such as alternate ports in place of the former non-designated port. Switches must be explicitly configured for a rapid spanning tree protocol in order to run the rapid spanning tree protocol. They should use RSTB to run the rapid spanning tree protocol. Now, as you see in this table, we have multiple different versions of a spanning tree protocol with a description of each one. Now, in T216B, you will study this in full details. Configuration will be covered as well. Mainly, we need to focus on these three versions. Now, rapid spanning tree protocol standards IEEE 802.1W supersedes the original spanning tree protocol while retaining backward compatibility, which means we stop using STB. We now implementing RSTB, but RSTB compatible with any existing network, for example, running the STB, the spanning tree protocol. 802.1W STB 1W STB terminology remains the same as the original .1D standards. So 1D STB 1W RSTB. Now, most parameters have been left unchanged. Users that are familiar with the original STB will be familiar and configure easily the RSTB. Same spanning algorithm is used in both to determine the port topology. But what's the main benefits now if mostly they are using same terminology, same configuration? RSTB or Rapid Spanning Tree Protocol increases the speed of recalculation. Recalculation will move from the blocking to the listening, learning forward state. So it increases the speeds of the recalculation of the spanning tree with layer 2 network topology changes. Simply, RSTP can achieve much faster convergence in the probably configured network, sometimes as a little of a few hundred of milliseconds only. If the port is configured to be alternate port, it can be immediately changed to the forward state without waiting for the network convergence. Now, let us have a quick comparison or discussion comparing some states on RSTP and STP. Now, we have only 3 port states in the rapid spanning tree protocol that corresponds to the 3 operational states. While how many states on the STP? 5. 4 operational, 1 non-operational. So 802.1d disabled blocking and listening states are merged into a single discarding state on RSTP standard. So on the STP we have disabled, blocking, listening state, all of them merged into a single state called discarding on a RSTP. Learning remain the same, forwarding is the same. Now, one more difference here on the right side. Root ports, designated port are the same for both STP and RSTP, but there are 2 RSTP port rules that corresponds to the blocking state of STP. Now, on the STP, we have root, designated, and blocked, non-designated. For the RSTP, 2 states corresponding to a single state of the STP, backup port and alternate port. And most widely now backup is not implemented, only alternate port. So the alternate port has alternate path to the root bridge. Simply, this is the root bridge, designated port, root port, sorry, it should not be designated, designated port, designated root port. Now this one is the alternate port. Backup, as you see here on S3, the backup port is a backup to share the medium, backup port to share something such as the hub. Backup port is less common because hubs are now considered legacy devices. Now, what's the fast port and the protocol, a bridge protocol data unit guard? When the device is connected to the switch port or when the switch power up, the switch port will go through both, listening and learning state. Each time the port will wait for the forwarding delay timer to expire. So what's the forward delay timer for the listening state? 15 seconds. What's the forward delay timer for the learning state? 15 seconds. What's the total delay time? 30 seconds in this scenario for every port when we switch or power up the port. So this can present what a problem for the DHCP client trying to discover a DHCP server because the DHCP dynamic host configuration protocol process may time out. So this results is that IPv4 client will not receive a valid IPv4 address because of the delay for the learning and the listening state. Now, if the switch port configured as port fast. Now, and the port fast should not be configured between the switches, only between the host and the switch, only. The port transition from a blocking to forwarding state will be done immediately if it's a port fast. Avoiding 30 seconds delay, you can use the port fast on access port only. So no need to wait for 30 seconds from a blocking to the forwarding state immediately, only on the access port to allow devices to connect to these ports to access the network immediately. So port fast should not be used, or sorry, should only be used on the access port. If you enable the port fast on a port connecting to another switch, a spanning tree loop. So all within the access port. So we can have a fast port in this scenario on this port, on this port, on this port, and on this port, between the host and the switch, because all of them are access ports here. Now, fast port enabled, a fast port enabled, a switch port should never receive bridge protocol data unit, because that would indicate that the switch is connected to a port, potentially causing a spanning tree protocol loop. So fast port should not receive any PPDU. So Cisco switch will support this feature or supports providing a feature called a bridge protocol data unit guard. When it's enabled, it will be immediately put the switch port in an error disabled or error disabled state upon receipts of any bridge protocol data unit. Simply, if it's a fast port and the port receives a bridge protocol data unit, PPDU guard will put the port on disabled state immediately. So this protects, or this solution protects against the potential loops by effectively shut down the ports. The administrator must manually put the interface back into the service in this case, because the interface will be disabled. Last is on module 5, alternatives to the spanning tree protocol. Over the years, organization requires a greater fluency or flexibility and availability in the LAN. Ethernet LAN went from a few interconnected switches connecting to a single router to very sophisticated and complicated hierarchical network design, including access, distribution, and core layer. Let me simplify to you the slides without reading everything, in case we have a very complicated structures. Layer 3 switches, mic please. Layer 3 switches. Now, in case we have multiple sophisticated switches, now it's recommended that we use a layer 3 between, let me say, the devices or the enterprise devices, the sophisticated devices, between the user and layer 2 network. Only at that layer we will use layer 2 switches. So layer 3 routing will allow redundant path and loop in the topology without blocking. Why? If we apply on the all layers layer 2 switch, we will not allow the redundancy, we will block any redundant link. So layer 3 will not blocking the redundant port. So it's recommended to implement only layer 2 switches at the access layer. User layer in other way. Simply. This is the main point to be delivered in this from this slide. Let me now stop the sharing. This is the end of 5. We are going to continue, okay, covering module 6. I will also stop the recording and I will